In our last lesson, we talked about how a variety of different fuel sources could be broken down through a series of oxidation reactions, with the electrons from those fuel sources passed on to NADH and FADH2, which could take those electrons into the electron transport chain. In the electron transport chain, these electrons got passed from one molecule to the next, pumping out protons as you went, and generating a powerful proton motive force, which today we'll see how it can be, that force, that gradient can be used to power the synthesis of ATP. This process is called oxidative phosphorylation, where we're coupling the phosphorylation of ADP to give us ATP to the oxidation in this electron transport chain that was being used to generate that proton gradient. Then we can use the proton gradients through this ATP synthase to make ATP. This is what we're going to focus on today, is this ATP synthase step, but we're also going to touch on a few other topics that come up. We're going to start with a review of the electron transport chain, make sure that we're all on the same page. We'll talk about that ATP synthase mechanism, so that's our complex 5. And then we'll talk about how things can go according to different plans or not according to plan. We'll talk about ways in which the gradients can get messed up, things like uncoupling agents. Some of these are natural, like our brown fat, which can generate heat. Some are unnatural and dangerous, like diet drugs, like DMP. And then we'll talk about when electrons kind of flow out of the chain instead of through the chain, generating reactive oxygen species, or ROS. A little bit of these can be a good thing, but a lot of them not so much. We'll talk about all these things and more, but this is what's in store. So let's go. Let's start by reviewing that electron transport chain. So let's talk about how we make ATP. This is this really awesome molecule, this really awesome protein complex, this ATP synthase. So this is complex 5. This is also called ATP synthase. Sometimes you might see it called like ATPase. It's kind of confusing because it's going to make ATP, but it can also break down ATP because remember, an enzyme is going to catalyze things in both directions. And it turns out that if you don't have this proton gradient powering things, well, then what you'll actually do is you'll see that you can get things moving in the opposite direction. But we're going to be talking mostly about the forward direction when we're making ATP from ADP, an inorganic phosphate. It's this totally beautiful molecule, and so I want you to go and take a look at the video. You might want to then rewatch the video after we go over the details to kind of let things sink in and contextualize things. But it's really this amazing machine. It's moving at things like 600 times per second or crazy speeds like that. We're really pumping out this ATP, and it's so beautiful to see. So go watch it. So as you saw in the video, you have these two distinct multi-subunit components. We have our FO or F0, this integral membrane protein, and we have this F1, which is going to be our peripheral membrane protein. Our F1, this is where we're actually going to have the active sites in these beta subunits. And it's going to have this central stalk, this gamma subunit, that's going to connect things to our FO. Our FO is going to contain this A subunit, which is where the protons are going to flow through, as well as this ring of C units, the C ring. The C ring is going to turn when the protons flow through A. This is going to then be coupled because this is connected, we have the B is then also going to be connected to our F1. Basically, when you have this ring turn, it's going to cause this central stalk to turn. When this central stalk turns, it's going to then lead to the kicking of the conformational changes happening in these F1 active sites. This is going to lead to the production of ATP. Well, actually, what it's leading to is kind of the release of ATP. One of the really fascinating things about ATP synthase is that the hardest step for it is actually releasing the ATP, so releasing the product. Normally, when we think about enzymes, we think about product release as being the fast step. That the hardest part was going and turning our substrate into our product. But then once we made that product, we'll just let go. Turns out that letting go is really hard for ATPase, this ATP synthase, because it binds to ATP really, really tightly. Binding to ATP really, really tightly, well, it enables it so that it's easier to make ATP, because you're getting basically the binding energy from binding to the ATP is going to make it so you'll have a lower transition state. This is going to make it so it's not as costly to make ATP as it would be normally. And in fact, you can actually go back and forth between ATP and ADP in the active site. But because it holds on to ATP so tightly, well, now it's going to be hard to let it go. How can you let it go? Well, you can let it go by changing the shape of that active site so that it doesn't have as high of affinity. In order to kind of coordinate that change, this is going to take place by having the movement of our FO, by the movement of the C ring, caused by the movement of protons, to cause the movement of the central stock, which is then going to kind of give a kick to the active sites that are holding onto the ATP. There's this idea, this theory, rotational catalysis, that is the name that we kind of give to this. In a little more detail, basically we had that F1 has three alpha and beta, three each of its alpha and beta subunits. The beta subunit, this is where we have our active site. The beta subunit can be in one of three conformations. The one that is, there's the one that holds on really tightly to ATP, this tight binding. Then we have the form and where it's like loose binding, it binds to ADP. And then we have empty, where it's very loose binding. So what we want to do is we're going to basically take the form, the conformation, the tight binding form, and we want to change it to the very loose binding form. And we can do this by kind of giving it a nudge. And we'll talk in a second about how we can give it a nudge. But when we give it a nudge, well, then we're not only nudging the one that we directly kick out that ATP, we're also going to cause a coordinated change through a cooperativity effect, where we're basically making the other subunits change their shape as well. Turns out that each of these subunits they have to be in one form, or like only one subunit can be in each of these forms. So they're all going to be in different forms, and they're going to take turns kind of who's getting to make ATP. As we'll see in a minute, it turns out that it takes 3 protons in order to do one of those, to make one of those conformational changes. So it's going to take 3 protons to produce an ATP. And you would have to go through a complete rotation of this cycle would then synthesize 3 ATP, because you had those 3 sites. But for each site, it would take 3 protons per ATP. And so why do we get this number that it takes 4 protons per ATP? That's because you have to spend a 4th proton in order to bring in another phosphate, another inorganic phosphate. In order to keep the cycle going, we need to bring in more inorganic phosphate, bring in more ADP, and in order to make the ATP that we made useful, we need to ship it out. This will also help keep our product levels low and our reactant levels high. As you can imagine, these negatively charged molecules aren't just going to flow through the membrane on their own. Instead, they're going to need help. So they're going to need to travel through membrane proteins. In the case of our ADP and our ATP, turns out we're going to swap them through the same transporter. So this would be an example of an antiporter, but because they're moving in opposite directions. Now, why are they moving in these directions? Well, we see that what we're doing is we're pumping out ATP 4- and we're bringing in ADP 3-. Based on charge alone, if we think about, remember, it's an electrochemical gradient, the electro part, we have things more positive on the intermembrane space, and therefore, and more negative on the matrix side. Therefore, if we pump out more negative charge than we bring in, from a charge standpoint, that's going to be favorable. And in fact, this is going to allow us then to do this swap. However, remember that the only reason that it was favorable was because we'd spent energy in order to pump out the protons. So although we're not directly seeing the protons involved here, that energy from the proton pumping was contributing. And so we're not changing proton concentrations on either side, but we are in effect dissipating the gradient of charge. So this is kind of costing us energy, but it's in an indirect way, and it's even more indirect than we normally think about when we think about our secondary active transport. Remember that our secondary active transport, we're driving something against its electrochemical gradient, driven by an ion moving down its gradient. Well, if we think about if we think about getting the phosphate in, well, here we're actually going to use that kind of more of the classical secondary active transport. In this case, we're actually going to take a proton from the intermembrane side where it's got this high concentration of protons as we've been pumping them all out, and it's going to co-transport that with our inorganic phosphate. They're both coming in, so this is going to be a symporter because they're going in the same direction. They're both coming in, and we're paying the cost of this inorganic phosphate coming in by using the gradient that we created. Because we're directly using this proton here, then we cost an extra proton per ATP that we produce. So we need those 3 to turn the pump, and then we need the 4th to facilitate the co-transport of bringing in this inorganic phosphate to keep things going. And then indirectly, that the gradient we're producing is also being used to power this other swap. But when we think about direct numbers for our accounting purposes, we typically just consider that there's going to be this one extra proton that you need, because that's the one that's going to be directly related to the transport of that inorganic phosphate. Whereas here, it's just like an indirect effect, and we're not directly transporting a proton, we're just changing the relative charges on the sides and lowering the electrochemical gradient that way. The electrical part, but not the chemical part. How are we going to, however, connect the movement of protons to the actual making of ATP? We connected it to the flow of the proton, of the inorganic phosphate, but really what we care about is how is that actual movement of protons going to be able to cause the making of ATP? It turns out that this is actually pretty cool. So in that A subunit of FO, so this part, remember FO, it's this integral membrane protein, so it's embedded in here. We have this A part. It kind of has these 2 little channels where one is open, these half channels. So one of these half channels is open to so in this case, again, it's upside down. So right here where we have a lot of protons, where is that going to be? Right, that's going to be in our inner membrane space. And then up here where we don't have as many protons, what's that called? Yeah, that's going to be our matrix. So we have the side that's open to the matrix and the side that's open to the intermembrane space. And each of these is kind of going to be, is going to come into contact with the C ring. So the C ring, we've got this, different species have variable numbers of these C subunits. What's going to happen is each of these C subunits has a binding site for protons. This binding site is either going to be a glutamate or an aspartate, depending on the species. So remember that each of these can basically give and take protons. We typically think about them as having given up protons, but you can imagine that if there's a lot of protons around, then they're going to be protonated. And where would you find a lot of protons around? Well, you find a lot of protons around in the inner membrane space. So when that glutamate or when that aspartate is exposed to the concentration of protons, so to the pH that's present in the inner membrane space, well, now it's actually going to protonate. But on the other side, when it's exposed to the matrix, where there's a low concentration of protons, well, there it's going to deprotonate. So if we can expose that critical residue to one side and then change and expose it to the other side, we can then transfer a proton from one side to the next. And in fact, that's what happens. So you have protons flow in. It can then protonate that key residue. That's going to interrupt interactions that residue had to another residue. And so basically, you're going to interrupt ionic interactions. When you interrupt things, then you kind of are going to cause a conformational change. This is going to drive the movement of this ring. So you get protonation. It's going to cause a conformational change. The conformational change is going to move the position of that key residue into the half channel where it can actually sense the environment in the matrix. When it senses the environment in the matrix, it's going to release the proton. In the process, you had this conformational change occurring. You had this movement of the ring, and the ring wasn't isolated. Instead, it was attached to these other parts of the protein. And so when this rotates, you get this rotation of the gamma subunit. And when the gamma subunit rotates, well, now it's going to cause conformational changes in the beta subunits of our F1. And those conformational changes in our F1, well, that's how we were going to be kicking out those phosphate, the ATP. So ultimately, we get this idea of rotational catalysis, where we have a rotation of the C ring linked to the production of ATP. Now let's do a little bit of ATP accounting. So imagine that we have NADH. It's going to come in complex 1. In complex 1, we're going to pump out 4 protons. And we're going to be passing a pair of electrons onto Q. That pair of electrons from Q is then going to go and it's going to travel to complex 3, and it's going to pass those electrons onto cytochrome C. In the process, it's going to pump out 4 protons. So we get 8 protons so far. That cytochrome C is now going to go and it's going to take those electrons to oxygen in complex 4. In doing so, it's going to pump out 2 protons. So ultimately, from our NADH, we got 10 protons pumped out. Now, we said that it took 4 protons to make an ATP because we had 3 to directly make it and then 1 to bring in the inorganic phosphate. So how many ATPs would we get from an NADH if that NADH was made in our matrix? Well, 10 divided by 4, we've got 2.5. But in the case of our FADH2, so remember that we're going to be going in complex 2. There we don't get those original 4 protons because we're not going through complex 1. So instead we get 6. We get 6 divided by 4 is 1.5. So we get about 1.5 ATP per FADH2. This ratio is something called this P to O ratio or this P to 2E minus ratio, 2 electron ratio. And so that's where we get this about 2.5 and about 1. And it's okay that we're getting these ratios and we're not really sure about numbers and things because remember, it's the gradient that's going to be doing the work. And it's not like there's a direct correlation between a number of NADH and the number of ATP. Instead, the NADH is contributing to this gradient. The FADH2 is contributing to this gradient. And ultimately, this gradient is going to be what's driving things. But it doesn't need to be like there's a distinct numerical ratio that makes total sense. So the gradient is being used to power the production of ATP. The production of ATP is directly coupled to the incoming protons. What would happen if ATP synthase was blocked? Well, if ATP synthase was blocked, those protons couldn't flow back through. If the protons couldn't flow back through, well, now you'd be building up the concentration of protons in this inner membrane space. This would make it so that it becomes harder to pump protons out. Remember that the pumping out of protons was powered by the pass-off of the electrons. By passing the electrons from something with a lower standard reduction potential to something with a higher standard reduction potential, you released energy. that energy was enough in normal situations to pump out the protons. But if the gradient is too great, then it costs too much energy to pump out the protons. You won't get enough energy from the passing of the electrons, and the pumping of the protons would actually stop. So ATP synthase, by letting the protons through, is making it so that we can keep pumping protons out. And if the ATP synthase was blocked and there wasn't another path through, well, then the pumping of the protons would stop. The pumping of the protons was directly coupled to the passing of the electrons. And so if the protons can't be pumped out, then the electrons can't be transferred. And if the electrons can't get transferred, well, then you're going to build up this NADH, this FADH2. And later we'll talk about how this NADH can then negatively regulate a variety of breakdown pathways, activate other pathways, and ultimately get things back to working conditions. Why might ATP synthase be inhibited? Well, there are a variety of drugs and things that you could use to artificially inhibit ATP synthase, but naturally ATP synthase can't function if it doesn't have that ADP. If you don't have ADP, there's nothing to power this passage through of the protons, nothing to power the ATP synthase actually going through its reaction. And so the protons aren't going to come through because the protons flowing through are directly coupled to the production of ATP. So if you don't have ADP, well, then you can't make ATP and you can't let these protons through. If you can't let these protons through, it's then going to have protons build up in this inner membrane space. If you have protons build up in the inner membrane space, you can't keep pumping protons out. Things are going to get backed up. Your NADH is going to build up, and ultimately your catabolism is going to be slowed. But now let's talk about the sort of opposite situation. What if we have the protons coming through a different way? So remember that our problem with our ATP synthase having a problem or being blocked was that we're going to build up these protons. That one of the functions of ATP synthase was to actually let those protons back through. What if we had another path for letting the protons through? In that case, we'd be able to continue pumping out the protons because we wouldn't be building up this super high gradient as we would in the case of this ATP synthase inhibition. If we do that, we can keep running the electron transport chain even if ATP synthase is blocked. So to keep the electron transport chain going, all we need is a way to let the protons back through. But to keep the ATP synthase going, well, there we actually have to have the protons flowing through this ATP synthase. If we don't have enough protons out here to flow through, then we're not going to make ATP, even if we could continue pumping protons out. So how could we get another path for the protons to come through? Well, we can talk about uncoupling agents. So we use the word coupling a lot when talking about oxidative phosphorylation, where we're coupling the production of ATP to the electron transport chain. Uncoupling agents make it so that the passage of electrons through the electron transport chain is not directly coupled to the production of ATP. That is, you don't have a sort of direct relationship. And the reason why this could happen is because you have another way for the protons to get through. That is, not all of your gradient is being used to make ATP. There are natural examples of this in our body, including this uncoupling protein, this UCP. This protein lets protons through. When you let the protons directly through, you're bypassing the making of the ATP, but you still get the energy that you would have gotten because you're going down the gradient of the protons. So you still get the same amount of energy, but here you're not actually using it to make ATP. Instead, it's given off as heat. This is a process called thermogenesis, and it can be used to generate body heat. Babies have a lot of this uncoupling protein because they have a lot of this thing called brown fat, which is rich in this UCP. Adults don't have as much brown fat. You lose it as you age, at least in the beginning, but we still have things called beige fat, which can have more of this UCP as well. So this uncoupling protein lets the protons through. You use the energy from that to generate heat rather than generating ATP. Good for some situations and good in small quantities in select tissues. But what would happen if you let protons through in a more uncontrolled manner, in a way that wasn't specific to those tissues and those locations where you needed heat, but rather was happening in all of your cells all the time and making it so that you couldn't make energy? This is the case with some chemical compounds that act as uncoupling agents. Most notorious is 2,4-dinitrophenol or DNP, which was marketed as a weight loss drug until they started realizing that it was killing people. And the reason that it was killing people was because it was acting as an uncoupling agent. Take a minute and look at the chemical structure of DNP, as well as this other uncoupling agent, FCCP. Highlighted in red is is a sort of hint. How might these compounds be able to take protons through into the matrix, through that inner mitochondrial membrane, bypassing the need for ATP synthase? Think about which has a lower pH, that is a higher proton concentration, the inner membrane space or the mitochondrial matrix? Right, the inner membrane space has a lower pH because you're pumping the protons out. In the context of that inner membrane space, would you expect that these compounds, therefore, would be in their protonated or deprotonated states? Right, we would expect them to be in their protonated states. In their protonated states, are they neutral or ionic? Right, they're neutral. And if you have these small neutral molecules with these kind of like benzene rings, these hydrophobic portions, well, they're able to pass through this inner mitochondrial membrane through simple diffusion. Once they're in the matrix, however, now we said that here, the pH was going to be lower. And once they're in the matrix, we said here, the pH was going to be higher. There were going to be fewer protons. At a higher pH, these are going to deprotonate. When they deprotonate, well, now they're releasing a proton in here, a proton that they took from out in the inner mitochondrial space. So they're transferring a proton from that inner mitochondrial space into inner membrane space into the mitochondrial matrix. And they're doing it without going through the ATP synthase. So they're dissipating the gradient, but not making ATP. To make things worse, once they're deprotonated, even though they're ionized, they have this sort of like resonance that makes it so that the charge is diffuse enough that they can diffuse back through the membrane, pick up another proton, and do this again and again and again, making them incredibly dangerous. So don't use them as a weight loss drug. Yes, you're burning energy without making ATP that could then be used to make fat and stuff, but you're also potentially going to die. So please, please, please do not use those. As we touched on briefly in the last video, rather than hanging out by themselves, these complexes typically chill together in these respiratomes. So basically, each of these complexes has a lot of different proteins, and then each of these complexes hangs out with one another, and you get these clusters of molecules in the membrane. This might remind you of when we talked about signal transduction, and we had multiple proteins in the pathway being kind of held together. One benefit of this was that it was then easier for things to find one another, more efficient. And another benefit in the case of the electron transport chain is that if the electrons kind of leak out, they can't get too far. In the electron transport chain, remember that we're ultimately passing off electrons to oxygen. What would happen if we didn't have oxygen around? Well, then there wouldn't be anything to accept, or we didn't have enough oxygen around. There wouldn't be anything to accept the electrons at the end. We'd just have a slowdown in our electron transport chain. If we have a slowdown in our electron transport chain, this can lead to the generation of reactive oxygen species, or ROS. So remember how Q, it could accept one electron, it can accept one electron or two electrons. And if it accepted one electron, we got this radical. And this radical was going to be generated in kind of like the normal process of things. But in the normal process of things, that Q was going to be kind of going straight from one thing to the next in that inside of the complex, and it wasn't going to be directly able to harm anything. It wouldn't be near any oxygen. All of that would be happening in this very controlled manner. But if there are holdups, it can kind of like escape. When you have that radical escape, well, then it can go and it can do things like cause damage. In order to prevent it from causing damage, our cells have different enzymes that can kind of counteract the oxidative stress. So we've got this like superoxide dismutase. We've got glutathione peroxidase. We have ways to take care of it. And it turns out that actually a little bit of reactive oxygen species can play an important role in telling your body we've got low amounts of oxygen. So I know it's a little confusing because, wait, we've got low amounts of oxygen, but we're generating reactive oxygen species. And that's because we don't have enough oxygen to keep this pathway moving really fast. And so we get these holdups. So then the oxygen that we do have, because it's not being reduced in this normal way, now it's able to react with those free radicals that are being that are leaking out up the line. Normally, however, the oxygen is going to be accepting the electrons. This is going to be used to pump out the protons. And all of this is going to be kept driven along at a nice pace because, well, then those protons are going to be flowing back through. Remember that this is happening through this really awesome complex, this ATP synthase, this tiny molecular motor. You don't need to worry about all of the details of this motor, but just the core idea that you have these two basic subunits, this FO and this F1. Protons flow through this FO, which drives the turning of this ring of subunits that's coupled to the movement of this sort of like inner rod that then causes the production of ATP in this F1 subunit. So you have this FO is in the membrane, protons flow through it. The flow of those protons along their gradient powers the turning of FO. The turning of FO powers the turning of this internal rod, and that ultimately causes ATP to be synthesized in this peripheral part, this F1 ATPase part. So really cool mechanism. You don't need to worry about all of the different details. Just the basic idea that we have the power from this proton gradient being used like a hydrolytic dam to turn the wheel, and turning the wheel is going to make it so that we're making and releasing this ATP. It's the release of the ATP that's the really hard part, but you don't need to worry about those nitty-gritty details. Just the fact that we have this coupling between the movement of those protons and the production of ATP. At the end of the day, we're able to make ATP efficiently this way.